talk about some results concerning classification results, concerning Delaunay surfaces, and also minimal surface as well. And I will describe some results for CMC surfaces, complete CMC surfaces in the Euclidean X-space R3, and some results about some pieces inside some balls in the Euclidean X-space R3. Okay, so let me start saying some words about the Delaunay surfaces. For us, Delaunay surfaces are simply complete rotational surfaces in the Euclidean X-space R3 with constant mean curvature. In this case here, Delaunay surface will be, in case, non-zero curvature, but we can, if we want, put together the minimal surface as well, rotational surfaces as well. In a very simple way, we can describe the Delaunay surface by a two-parameter family of surfaces in the following way. We consider these two parameters, age, a positive constant, and b, non-negative constant, b different from 1. And we consider as a curve. This curve here is in the xz plane, with in this first moment here the x function is a positive function. Then a Delaunay surface can be described by this parameterization here, where x and z are given by those functions here, right? This is the very simple way to describe a Delaunay surface using these two parameters, b and age, right? And so I'm putting this way because in a few moments I will describe some classification results, and I will use this this parameterization in order to describe the result, right? So what Delaunay surface is this surface described by these functions, and when b is positive and less than 1, these Delaunay surfaces are embedded, and they are called unduloids. If this constant b is greater than 1, they are only immersed and called nodoids. And if we think about the surface when b is equal to 0, this is exactly the right cylinder. And when b goes to 1, they converge to a string of tangent spheres with the same radius. Okay, so this family is the family of surface we are interested here, right? Just to put some pictures here, the rotational CMC surface, including the minimal surface, we have these planes, carotenoids, spheres, and right cylinders, right circular cylinders, unduloids. Unduloids when you take the parameter going to 1. Here is the spheres in this string, and the nodoids, right? So those surfaces are very important, especially when you are considering the unduloids, because the unduloids are very important when you are studying embedded CMC surface with finite topology, right? In fact, Korevac, Kuznet, and Solomon proved that when you have a CMC surface with finite topology, I mean with genus and k-ends, finite k-ends, these k-ends exponentially are exponentially asymptotic to Delaunay unduloids. And this decayment condition is very interesting because you can obtain some classification, characterization results exploring this kind of decayment condition. Okay. Previously, Mix proved that, in fact, spheres are the only properly embedded surface in R3 with non-zero constant mean curvature, finite topology, and at most one end. And using this result proved by Koreva, Kuznin, and Solomon, is it possible to prove that the only CMC surface, annular surface, is the Delaunay surface? Actually, let me see, not say annular, but a complete embedded CMC surface having two ends, then this is an unduloid. In the previous result, they put it properly embedded, but actually just embedded is enough for this result. As I said, this exponentially asymptotic behavior of the ends is very interesting because you can obtain this kind of characterization. So let me present one result more obtained by more recently, proved by Barbosa and do Carmo. Barbosa and do Carmo proved that the regular algebraic surfaces in R3 for actually just spheres, right cylinders, right circular cylinders, and planes. Actually, this result was proved by Oscar Perdomo in 2010, assuming this surface is a level set of a polynomial function with degree 4. And so regular algebraic surface here is in the sense that the surface is a level set of a polynomial function, and this level set, the gradient of this polynomial function is not zero along this level set. This is what do I mean by regular algebraic surface. So Perdomo proposed this problem to study the level sets of polynomial functions, and he was able to prove this result for polynomial functions with degree 4, and Barbosa and do Carmo proved this result for a more general situation. And the strategy followed by Barbosa and do Carmo was exactly consider the ends of the CMC surface and explore this exponential decayment, exponential asymptotic condition of the ends, and prove that, in fact, if the curvature is non-zero, this surface should be a right circular cylinder. A very interesting question that we arise here is it because, look, an sphere and a right cylinder, or planes as well, are level sets of polynomial functions. But actually, you can see those surfaces, for example, that are level sets of homogeneous functions, or functions that are separable of type of separable of variables. So it's interesting to consider this problem and to classify the level sets of some types of functions a little bit more general, or a little bit different from the polynomial functions. And very recently, Rafael Lopes and Hazanis studied this problem for separable variable functions of separable variables, functions like this. And if you consider a function like this, the level set where the gradient has all the coordinates different from 0, then it should be Delaunay surface. Actually, it should be Delaunay surface. And of course, planes and catenoids satisfy this condition as well for special functions. And as I said, this problem is very interesting because you can explore this asymptotic behavior of the ends. And what we would like to do is exactly this, explore this kind of decayment. But look, if you consider a level set of a smooth function, the second fundamental form, the mean curvature, the curvatures, the support function, are given by the derivatives of this function f here. So if you have a kind of control for the derivatives of the function, the control of the derivatives of this function f, you will have controls on the geometry of the surface, the level set sigma. Okay, so we would like to extend the set of functions which we can study the level sets more than polynomial functions, or more than the separable or variables functions like this one, exploring this situation here. We take a function f with a kind of control in its derivatives, and then we get a control in the geometry or in the topology of the surface, and then try to classify this surface. One example of this is if you consider, for example, the catenoid. Catenoid is given by this equation here and this function. If you explore the derivatives of this function in order to get the second fundamental form of the catenoid, you will see that the second fundamental form has this decayment here. So we will say that a minimal surface in the Euclidean space satisfied has the quadratic decay of curvature if the second fundamental form satisfies this inequality here. Okay, so the catenoid is one example of this situation. So we would like to do exactly this, take a surface level set of a function, depending of the control of the derivative of the function, you will have a kind of control in the geometry of this surface. And is it possible to get a control in the topology and then classify the surface? Mix, Paris, and Ross in 2008 proved this result here. If you consider a surface, minimal surface in this case, connected in and embedded, satisfy this quadratic decay of curvature with the constant c equal to 2, then this surface should be either a plane or a catenoid centered at origin. Okay, so if you have a function f, consider the level set of this function, compute the second fundamental form. If you have a kind of decayment like this, then you will get a classification result. It should be the plane or catenoid with the center at the origin. So, of course, this is a result for minimal surface. And the question is, and we can do this for CMC surface. And let me extend this concept of quadratic decay of curvature for this CMC surface situation. So we will say that a surface in R3 is a surface that has quadratic decay of curvature if this inequality here is satisfied by the surface. where this is the umbilic tensor of the surface, and this is the support function. Actually, you can put here the normal of x, normal square of x, and we can say the same. Quadratic decay of curvature will give this inequality here. And if you are with a minimal surface, you will see that this quadratic decay condition is the same as above. Okay, and the circular cylinder is an example of a CMC surface satisfying this quadratic decay of curvature here. Of course, the sphere satisfies this as well, because the spheres are umbilic. And this will be 0, and this is a non-negative number, and then this is true for the spheres. Okay, so with this kind of quadratic decayment of curvature, we were able to prove a kind of classification result involving this Delaunay surface. Actually, we proved that if this is the exactly situation for the minimal case. If you have a surface connected, complete and embedded CMC surface. In this case here, we will assume the CMC surface is non-minimal surface, because for the case of minimal surface, this is exactly the situation proved by Mix, Perez, and Ross. But yes, here we are assuming this CMC surface satisfies this quadratic decay of curvature with the constants A equal to 1.5 and B equal to 2. Then just the spheres and right circular cylinders satisfying this quadratic decay of curvature here, with A equal to B and A equal to 1.5 and B equal to 2. Okay. Let me give a simple, in a very in a few steps, the idea how can we prove this result. The idea is the same explored by Mix, Perez, and Ross. The difference is just this the decayment condition. For the minimal case, we will see in a few seconds, it's enough, directly enough to see this function, the distance function, exterior distance function, is a convex function. But for the CMC case, we have to explore a little bit more the complex structure of the CMC surface in order to prove the same will be true. This function here will be a convex function. To be a little bit more precise, if we consider this distance function on the surface, when we write the Lorentzian of this function here, we get that the eigenvalues of the Lorentzian function are given this way. Here, K1 and K2 are the principal curvatures of sigma, right? So, so now, if you take the product of these two eigenvalues, we get that this product is given by this expression here. And this expression here is greater than or equal to 0 because of the quadratic decayment condition of the curvature we are considering, right? So this gives us that the product of these two eigenvalues have the same sign, right? So if we prove that the sum of these two eigenvalues has a sign, then they have the same sign. Okay. If, for example, if the sum is positive, at least one of these numbers should be positive, and then both of the numbers are positive. Okay. If we assume this function here change sign, we will find one point where this function is 0, And then this sum here is 0 in this point. And this will imply that this point where this function is 0 is an umbilic point to the surface. This is because, of course, if this is 0, this function here, support function, cannot be 0. And this is 0. This product should be 0. And then this function here, the norm of the umbilic tensor should be 0 in this point. So this point is an umbilic point. And because of the complex structure of the surface, this umbilic point is an isolated point. And so we can explore this situation in order to prove that this point where this function is 0 cannot exist. And so this function here has a sign. We can assume without generality is a positive function. And then at least one of these eigenvalues should be positive. And then lambda 1 and lambda 2 has to be non-negative. And then the range of this function is non-negative. This function is a convex function. So you have found a convex function on the surface, and then we can analyze the set of global minimal points, the minimal points of this function. And so we define this set here and consider this set of minimal points of this function. And because of the function is a convex function, this set is totally convex in the sense that if you take 2 points in C, every geodesic connecting these 2 points should be inside this set C here. Right? Okay, so if this set contains just 1 point, then the function phi is a convex function with only one global minimal point. Then is it possible to use Morse theory in order to prove that this surface should be a simply connected surface, right? So in this case, we can use the result proved by Mix and Tinaglia in 2006, that the round spheres are the only complete simply connected surface embedded in R3 with non-constant mean curvature. Then in this case, if this set has just 1 point, we get the surface should be around the sphere. Okay. So now, if this set, suppose this surface is not totally simply connected. In this case, this set has more than 1 point. Yeah, because if it has just 1 point, it should be simply connected. Then we prove that this, just because of the convexity, this set here is a closed geodesic, connected, and is a closed geodesic. We can just now explore this situation in order to prove that the fundamental group of the surface is cyclic, because actually, if the surface is not simply connected, you take non-trivial class. Okay, you consider the fundamental group based in a point in C. You take non-trivial class, and then in this non-trivial class has geodesics, and then you can prove that this geodesic is exactly this curve C here, because the convexity of the function phi. And then this fundamental group is cyclic, and this surface is an annulus. And now we can use this result proved by Mix and Tinaglia, also in 2006, that the only complete annulus embedded, CMC embedded with non-zero constant mean curvature is the right cylinder or an unduloid. Unduloid because it's embedded. So what we should do now is to prove that the unduloid cannot happen, right? So we prove that it's the surface should be is either a round sphere, a right cylinder, or an unduloid. And what we can do now is what we have to do now is to prove that the unduloid cannot happen. And this, okay, we take a surface, a Delaunay surface with parameter between 0 and 1 is an unduloid. And we take a parameterization for it this way. And because we are in this situation here, the derivative of this coordinate z is positive. The function z is an increased function. And now we choose some special points in this surface in order to make the function z goes to plus infinite. And why we are doing this? Just because if we take the this parameterization here, parameterization for the unduloid, you can compute directly the eigenvalues of the function phi, the distance function, what the square of the distance function, and those eigenvalues are given by this equation here. Actually, in those points, the first one is 1, and the second one is given by this expression here. And if the z function evaluated in this point Tn, choosing as we have done, this function is going to plus infinity, and then we can obtain that when this index is very big, this number here is negative. Then the product of these two eigenvalues is negative, and this is enough. This is enough to say that the quadratic decay of curvature is not verifying by this equation, this surface. Just because when the quadratic decay of curvature is true, then the product of these eigenvalues are non-negative, right? So this is to prove that the unduloid cannot happen. Actually, the unduloids do not satisfy this quadratic decay of curvature. Then we obtain that for the case of CMC surface, connected, embedded, complete, satisfying this quadratic decay of curvature, should be just the spheres or right circular cylinders. Okay, so if we look at for this result for high dimension, is it possible to prove this, considering this decay quadratic decay of the curvature here? But we were not able to prove that when the simply connected condition, the simply connected situation being verified, we were not able to prove that this is a plane. But for the case of the circular situation, the annular situation, the surface should be catenoid inside a three-dimensional linear space R3. And in order to prove this result, we perform the same idea as Mix, Perez, and Ross, the minimal case. And we have to use a kind of reduction, dimension reduction argument in order to get inside a three-dimensional space. And this we have to do analyzing modal sets of solution of elliptic system of partial differential equations. But anyway, we can obtain the same kind of result for surface with very high codimension. Okay. The question here is it possible to prove a result like this for the case of CMC surface involving the Delaunay surfaces. And this is a result we wasn't able to prove yet. Okay, so but we have some kind of result, partial result, but it's not an interesting result yet. Okay, so so now let me remind you that we have proved there exist unduloids that doesn't satisfy this quadratic decay of curvature, and we can prove as well that there is pieces of nodoids inside balls which satisfies this kind of quadratic decay of curvature. Okay, so the question here is, okay, if you are inside a ball, the pieces of nodoids are the only CMC surface satisfying that kind of quadratic decay of curvature. Of course, piece of nodoids and piece of spheres as well. This question is a question, not just a question in order to extend the results, but this question is connected with some classical results in the unit spheres. Actually, if you consider surface in the unit spheres, we have these two classical results. The first one due to Chen Kobayashi, Dukarm Kobayashi, Nansen. For the case of minimal surface, closed minimal surface, if you have this gap condition here for the second fundamental form, this surface should be an equator, totally geodesic, or a Clifford torus, a Clifford tori. For the CMC case, you can consider this polynomial function here involving the mean curvature of the surface, and the root of this function, this polynomial function here, you can use to construct this kind of quadratic decayment of curvature here. And the only surface satisfying these conditions are the totally umbilic surfaces, hypersurfaces, and the AGR torus, a kind of Clifford torus for the CMC situation. This is what was proved in this sphere. If you think about this kind of result for free boundary or pieces, surface inside the balls with free boundary condition, I mean, with the boundary meeting the boundary of the ball in an orthogonally way. Of course, you can think about this as well for the capillary situation, more general situation, but let's focus on the situation where the angle of contact is pi over 2. Okay, so if you think about this result for the free boundary situation inside a ball, the first result presented connected with this question is this result here, proved by Ambrosio and Nunes. And it's the same quadratic decay of curvature considered by Mix, Perez, and Ross for the complete situation inside the R3. But now you can perform the same idea in order to get this surface should be simply connected or has a topology of an annulus. But now you don't have this result of classification. Actually, you can use a type of unique continuation result in order to get that this surface, when that set of minimal points are geodesic, closed geodesic, is this will be a critical catenoid, and for this case here will be a equatorial disk. But Ambrosio and Nunes don't use this argument first for considering this unique continuation argument. They used another argument that is very useful in another situation. They used this result due to Chang that the nodal sets of a function, Jacob function, would contain only isolated critical points. So what they have done was they considered a rotational function for this second situation here. And this rotational function is a Jacobi function, but that set C, the critical points of the function phi, is inside this nodal set. And then the function has to be zero, a null function. And then the surface is a rotational surface. And then you can obtain this is the critical catenoid, right? It's the critical catenoid. A piece of a catenoid inside a ball meeting the boundary in an orthogonal way. And if you consider the situation for the CMC surface inside the ball, free boundary condition, and this quadratic decay of curvature condition here, we can do the same. We prove that the surface should be a spherical cap or a piece of a Delaunay surface. But now we cannot avoid the situation to be a piece of unduloid. Okay, so because we know that inside the ball there is piece of nodoids satisfying this quadratic decay here, and there exists piece of unduloids that doesn't satisfy this. So we don't know exactly what kind of piece of Delaunay will be the guy satisfying this condition here. Okay, because of course can exist a piece of unduloid inside the ball satisfying this as well. We just know that there exists piece doesn't satisfy. Okay, so but here we have to use this result of Chang because we don't know a model of a surface in order to use this unique continuation argument that is enough for the case of minimal surface. Here we have to use exactly this kind of Chang result because the CMC case we need this, right? So anyway, in order to, here we have the spherical caps and the piece of Delaunays. And just to finish this part here, and I won't spend much time here, is it possible to deal with this situation for high dimension? The quadratic condition here with this number will imply the surface is a totally geodesic hypersurface, actually. But we weren't able to find a quadratic decay condition good in order to take the catenoid in this classification result. Okay, a little bit. Let's think about the characterization of CMC annular, just annular surfaces now. Okay, not in a general situation. This result, proved by Mix and Chinaglia in 2016, classify all the complete annulus embedded in R3 with constant mean curvature. It should be catenoids or Delaunay surface. The question here is it possible to classify the complete free boundary surfaces, CMC surfaces inside the ball? Because of course, the argument for the complete situation is a little bit different from the capillary situation or free boundary situation. And so there is this conjecture here that the critical catenoid for the minimal situation is the only embedded free boundary minimal annulus in the ball. This result was somehow announced in this classical work of Nietzsche, but was recovered by Fraser and Lee in recent work. But anyway, this is conjectured for the minimal case. But we can include this kind of question. I mean, is it possible to classify the annulus, CMC annulus, free boundary CMC annulus in the unit ball? Well, let me present some partial results. Here we have this very classical result due to Vent. Actually, Vent worked with CMC surface inside a slab, but of course, if you are in the situation where the embedded annular capillar surface in the ball has the boundaries as planar curves and the planes are parallels, then it should be a piece of a Delaunay surface. Of course, we are assuming here this surface is embedded. Pew in 2009 proved this result, not assuming that the planes are necessarily parallels. But if the surface has at least one umbilical point, then this surface should be a piece of a sphere, right? It's like you consider a sphere and cut the sphere by using two parallel planes. Another interesting result is this one, proved by Ross. Ross and Swan proved that if you have an annular embedded free boundary CMC surface in the ball, then a kind of two-piece property verified for this surface. I mean, every plane in a tree passing through the origin divides the surface in at least two connected surfaces. Actually, the result is the surface does not lie in a half ball. So every plane passing through the origin divides the surface in at least two connected surfaces. The question here is, can we conclude that these planes through the origin divides the surface in exactly two connected surfaces? Exactly. Here I wrote this in the wrong way. Okay, this would be a kind of the two-piece property for the free boundary CMC case, because for the minimal case, it was proved recently by Wanderson Lima and Ana Menezes. And this kind of property is very interesting because you can explore this property in order to classify surfaces inside a ball, right? Actually, this kind of result was proved in this sphere and was very useful to prove classification results in this sphere. And here is the same. Okay. What is interesting, I'm mentioning these results here because, of course, we have many other results we can put here, but I chose this one because they explore a technique of moving planes. Moving planes techniques can be explored in order to get these results here. And the philosophy of the moving planes, Alexandrov reflection technique, is the symmetry. For example, the symmetry of the symmetry of the boundary can reflect to the symmetries inside the surface. So we expect that this Alexandrov reflection technique should be enough in order to get this kind of classification results. Okay, so just to mention another results here, Pew proved actually if one of the boundary components of the free boundary minimum annulus is a rotational symmetric, it's a planar curve, for example, then up to rigid motion of the ball, sigma is the critical catenoid. This is an application of the Jorling uniqueness result. And yes, so there is this another one proved by Tran and David. involving the Morse index of this surface, right? So if the surface is an annular embedded free boundary minimum surface with Morse index 4, then it should be the critical catenoid. These two results are very interesting because they use the very important result proved by Fraser and Shane, that is this one, an immersed minimal free boundary minimal surface, annular minimal surface. The number one, actually not just for annular, number one is eigenvalue of the Steklov problem. Steklov problem is this one. But if one is exactly the first Steklov eigenvalue, then this surface should be the critical catenoid, is the critical catenoid. And this result was explored by Tran and David in order to prove this result for considering this Morse index condition here. And also, McGrath proved this another result here, considering a more geometric condition. He proved that if the embedded free boundary minimum annulus has this symmetric condition, symmetric with respect to the coordinate planes, then this minimum surface should be the critical catenoid. And the idea of McGrath was just to explore the symmetric condition in order to prove that the first eigenvalue of this Steklov problem is exactly 1, and then he can use the result proved by Shane. So as I said, if you look at the philosophy of the moving plane technique or Alexandrov reflection technique, the idea is the symmetry of the boundary can pass to a symmetry of the surface. So is it possible to prove that this actually this result proved by McGrath, he assumed the symmetry of the surface with respect to the coordinates planes, but you can assume the symmetry of just for the boundary with respect to the 3 coordinate planes, and then you use this Alexandrov reflection technique in order to prove that actually the surface is symmetric with respect to the coordinates plane. And then this is enough in order to prove that this surface is the critical catenoid. So now I'm mentioning this because this Alexandrov reflection technique, the moving plane technique, it's very, we can use in order to get many results. And this result here, for example, let me say, if you have a kind of, I'm saying this angle symmetry, that is, if you consider the gradient of the distance function, the gradient of the support function, if these functions are, these vectors are multiples along one of the component of the annulus, then the surface should be the critical catenoid. This is another kind of symmetry for the boundary you can explore in order to prove the surface is the critical catenoid. But just to mention here, McGrath proved very recently, exploring that kind of two-piece property for free boundary situation, that the surface, if it has this antipodal map symmetry, then this surface should be the critical catenoid. Then, in order to prove kind of classification result for the Delaunay surfaces inside the ball, pieces of Delaunay surface, maybe this Alexandrov reflection technique can be useful, as it was useful for Ross and so on, to prove kind of two-piece property. Maybe is it possible to be explored in order to prove a classification result for the CMC case, right? So this is what I want to do, and mention this: the moving plane principle, the philosophy of Alexander Grafation technique is the symmetry at the boundary can be promoted to the symmetry in the interior. And so maybe this can be very useful in order to prove another results involving, for example, the CMC surfaces, the Delaunay surface inside a ball. Right, this is it, and I will finish here. Thank you very much.
Thank you, Ezequiel. So if there is any question now or any comments?